Hey everyone, and welcome to this explainer. Today, we are completely demystifying powers, exponents, and square roots. We're going to stop treating these like boring, rote algebraic rules, and instead we're going to explore them for what they really are, the elegant, totally logical building blocks that actually power the geometry of our world. So let's just dive right in.
Here is our roadmap for today. We are going to start with the basics of powers and exponents, master those core rules, and then look at reversing operations with square roots. After that, we'll cover working with those roots, highlight some common mistakes to avoid, and finally, wrap up with exactly why this math physically matters in the real world.
All right, Section 1. Basics, powers and exponents. To kick things off, we really need to ask a fundamental question. What exactly is a power at its core? Because, nailing down this terminology is the absolute key to unlocking all the patterns that follow.
Well, powers aren't just arbitrary, made-up math. They're actually a highly efficient shorthand for repeated multiplication. Take a look at 2 to the 4th power. That large number, the 2, is what we call our base. And that small floating number, the 4, is the exponent or the power. Think of that tiny 4 as a little instruction manual. It's basically saying, hey, take the number 2 and multiply it by itself exactly 4 times. So 2 times 2 times 2 times 2 gives us 16. It's just a brilliant way to save time and space on the page.
And this shorthand anchors directly into the physical geometric world. When we raise a number to the power of 2, we actually call it squaring. Why? Well, if you have a physical square with side lengths of 5, finding the area means multiplying 5 by 5, 5 squared. And when we raise a number to the power of 3, we call it a cube. A 3D box with sides of 3 has a volume of 3 times 3 times 3, or 3 cubed. Math here is literally just a language describing physical reality.
Moving on to Section 2, mastering the exponent rules.
Okay, let's look at the core rules, which are honestly just simple patterns. When you multiply two terms with the same base, you just add their exponents. Think about it. If you have 2 cubed times 2 to the 4th, that's just 3 2's multiplying against 4 2's. Join them all together, and you have 7 2's, 2 to the 7th. It's literally just counting. Conversely, division cancels factors out, which means you just subtract the exponents. And a power raised to another power, that multiplies the exponents together. You're just stacking operations. Easy, right?
So the really crucial point here is this logical pattern. Let's trace it downward. 2 to the 4th is 16. Drop the exponent by 1, and 2 to the 3rd is 8. Drop it again, 2 squared is 4. 2 to the 1st power is 2. Notice what's happening. Every single time we decrease the exponent by 1, we divide our answer by 2. So following this flawless logic, what logically comes next when we reach 2 to the power of 0?
The answer is 1. Any non-zero base raised to the power of 0 is simply 1. Think about it. If 2 to the 1st power is 2, and our pattern dictates we must divide by 2 for the next step down, then 2 divided by 2 equals 1. It's the completely unavoidable consequence of this mathematical pattern.
But wait, what happens when exponents go negative? A lot of people think it creates a negative number, but no, the pattern just continues by dividing. If 2 to the 0 is 1, stepping down to 2 to the negative 1 divides by 2 again, making it 1/2. 2 to the negative 2 is 1/4. 2 to the negative 3 is 1/8. Dipping below 0 logically just drops the number straight into the denominator to create a fraction.
Let's watch these rules tag team a more complex problem. Say we need to simplify 2 cubed raised to the 4th power, and all of that is divided by 2 to the 5th. Step 1. Apply that power of a power rule on top. 3 times 4 is 12, giving us 2 to the 12th. Step 2. Set up the division. We now have 2 to the 12th divided by 2 to the 5th. Step 3. Apply the division rule. Since the bases are exactly the same, we just subtract the exponents. 12 minus 5 is 7. Our final answer is 2 to the 7th, which equals 128. As you can see, complex problems are really just stacking simple rules on top of each other.
That brings us to Section 3, reversing operations, square roots.
We've seen how to build numbers up through squaring and cubing. But what if we want to hit the undo button and tear them back down to their roots? What does that famous jagged checkmark symbol actually mean in practice?
Well, a square root is simply the direct opposite of a power. When you see the square root of 25, the math is asking you a very specific question. What non-negative number, when multiplied by itself, gives me 25? And the answer, of course, is 5. Now, you really want to notice that term non-negative. Mathematically, the square root of x squared equals the absolute value of x. While both 5 squared and negative 5 squared equal 25, the square root symbol strictly asks for the principal non-negative root.
So here we have perfect squares. These are integers multiplied by themselves to create numbers like 1, 4, 9, 16, and 25. Therefore, their roots fall perfectly back into whole numbers like 1, 2, 3, 4, and 5. Memorizing these specific perfect squares is the ultimate benchmark, and honestly, it will save you an immense amount of time down the road.
Section 4. Working with square roots.
Now, what do you do when you step into the messy reality of a non-perfect square, like 20? You break it down into bite-sized pieces. Look for the largest perfect square factor. 20 is exactly 4 times 5, and we already know the square root of 4 is 2. So we can just pull that 2 right outside the radical sign, leaving the 5 inside. It beautifully simplifies down to 2 times the square root of 5.
And this reveals an absolutely fantastic mathematical secret. Roots and exponents are actually the exact same language, just written a little differently. A square root of x can simply be written as x to the power of 1/2. A cube root? That's just x to the power of 1/3. All the exponent rules we learned earlier apply perfectly to fractions too. It is all one unified logical system.
Section 5. Common mistakes to avoid. Let's set up some guardrails.
This is mistake number 1, and look, we have all done it. Working fast, your brain sees a 2 and a 3 and just assumes multiplication. 2 cubed is absolutely not 2 times 3. Remember, an exponent is an instruction for repeated self-multiplication. It's 2 times 2 times 2, which gives us 8. Always pause for a second and remind your brain what that tiny floating number really demands.
Next up is a highly misunderstood nuance. If an algebraic equation says x squared equals 36, then x could indeed be positive 6 or negative 6. Both of those work. But if you see a radical symbol, just the square root of 36 written out, it is strictly asking for the principal root, the non-negative root. The answer is just 6, not plus or minus 6. Keep those two concepts distinctly separated in your mind.
And finally, please never split addition underneath a square root. If you have the square root of the whole expression, 9 plus 16, you absolutely cannot separate that into the square root of 9 plus the square root of 16. Look at what happens if you try. You get 3 plus 4, which is 7. But if you combine the numbers correctly first, 9 plus 16 is 25, and the square root of 25 is 5. 7 does not equal 5. Always, always combine your addition under the root first.
Let's bring it all home with Section 6, why this math matters.
So zoom out for a second. Why do we actually care about all this? Because these simple building blocks construct our physical reality. You literally cannot navigate geometry without squares and roots. To find the diagonal length of any rectangle or triangle, you rely on the Pythagorean theorem, which requires taking the square root of a squared plus b squared. Exponents are how we calculate the area of circles, the curve of a satellite dish, and even the trigonometric waves of light and sound bouncing around you right now. By mastering these simple rules today, you've just been handed the keys to unlock the next mathematical dimension. So, what cosmic patterns are you going to decode next? Keep wondering, keep calculating, and I'll see you in the next explainer.